Consciousness. You are aware of yourself reading these words right now. Or rather, you are aware of yourself hearing these words. There is something it is like to be you. In this moment, the sense of presence, of interiority, of being the particular consciousness that you are, rather than any other. This fact is the most immediate and certain thing you know. You cannot doubt that experience is happening, because doubting is itself an experience. And yet, it is the one thing that science, despite extraordinary progress in every other domain, has been almost entirely unable to explain. The neuroscience of the brain has advanced remarkably. We can identify which regions activate during different mental processes. We can watch memories form in real time. We can map the networks that underlie attention, language, emotion, and decision-making. We can describe, in considerable detail, the functional architecture of the mind. But there is a question that all of this functional description leaves completely untouched. Why does any of it feel like anything? Why is there a subjective experiences accompanying these physical processes? Why isn't there just computation in the dark without any experience of that computation, without anyone home? Philosopher David Chalmers named this the hard problem of consciousness in 1995, distinguishing it from the so-called easy problems, the functional questions about attention, memory, and behavior that neuroscience can in principle address. The hard problem is not about what the brain does. It is about why the brain's activity is accompanied by experience at all. The standard scientific framework assumes that everything about the mind can eventually be explained in terms of physical processes in the brain. But no one has yet provided a convincing account of how physical processes, neurons firing, chemicals diffusing, electrical signals propagating, give rise to the felt quality of experience. The redness of red, the painfulness of pain, the specific sense of what it is like to be you, here, now. Some philosophers and scientists have had that consciousness is a fundamental feature of reality, present in some basic form, even in elementary particles, and that the brain does not generate it, but rather organizes and amplifies it. Others maintain that consciousness is entirely a product of sufficiently complex information, processings, and will eventually be explained in those terms or fruit. Others believe it is genuinely irreducible, something that cannot be captured by any physical or computational account, however complete. No one knows. The most intimate fact about your existence, that you experience it, remains the deepest unsolved problem in all of science, dark matter, and dark energy. The universe, as best as modern physics can determine, is made of approximately 5% ordinary matter. The atoms, molecules, planets, stars, galaxies, gas clouds, and black holes that constitute everything we have ever directly observed or measured account for, roughly 1 part in 20 of the universe's total content. The remaining 95% is something else entirely. About 27% appears to be dark matter, a form of matter that has mass and therefore exerts gravitational influence, but does not interact with light in any way we can detect. It does not emit light. It does not absorb light. It does not reflect light. It is invisible to every telescope and detector we have ever built. We know it exists because of what it does to the things around it. Galaxies rotate in ways that only make sense if there is much more mass present than we can see, and light bends around apparent empty space in ways that indicate something massive is there. But what dark matter actually is, what kind of particle or field or structure it consists of, remains completely unknown. Decades of increasingly sensitive experiments designed to detect it directly have found nothing. Physicists have proposed dozens of candidate particles. None has been confirmed. The most commonly searched candidate, the weakly interacting massive particle, or WIMP, has been hunted in deep, underground laboratories across the world and has not been found. The remaining 68% of the universe is something even stranger. Dark energy. This is not matter at all, but appears to be a property of space itself. A kind of energy inherent to the vacuum that is causing the expansion of the universe to accelerate. Space is not just expanding. It is expanding faster and faster. The galaxies are not just moving apart from each other, they are accelerating away from each other. As though some invisible force is pushing the fabric of the universe apart from within. Einstein's equations of general relativity embodied dark energy through what he called the cosmological constant, a term he originally introduced and then famously called his greatest blunder, because it seemed to require energy to emerge from nothing. It turns out the universe actually needs something like it. But what that energy is, where it comes from, and why it has exactly the value it has, remains entirely unexplained. The universe is mostly made of things we cannot see, cannot detect directly, and cannot explain. The 5% we understand is the exception, not the rule, the origin of life. Somewhere between 3.5 and 4 billion years ago, on a planet that was geologically violent, bombarded by asteroids, and bathed in ultraviolet radiation from a young sun, chemistry became biology. A collection of molecules, carbon, hydrogen, oxygen, nitrogen, phosphorus, organized themselves into a system capable of two things that no chemistry before them had managed: making copies of themselves and using information encoded in those copies as to build structures. How this happened is one of the most profound and most contested questions in all of science. We know the raw materials were present. We know the conditions: volcanic tidal pools, ice-covered lakes, the atmosphere itself provide energy sources and chemical gradients that could, in principle, drive the formation of complex molecules. Experiments dating back to Stanley Miller and Harold Urey in 1953 have demonstrated that amino acids, the building blocks of proteins, can form spontaneously from simple chemicals under conditions that simulate early Earth. But the gap between amino acids and living cells is vast. A living cell is not just a collection of complex molecules. It is a self-maintaining, self-replicating, information processing system of extraordinary sophistication. The simplest known living organisms have hundreds of genes and thousands of proteins, all working in coordinated networks that we still do not fully understand. even after decades of study. The central chicken and egg problem of life's origin is this. Proteins are needed to replicate DNA, but DNA is needed to make proteins. Neither can function without the other. Which came first? And how did the system that requires both ever get started? The most widely supported current hypothesis proposes that RNA, a molecule that can both carry information like DNA and catalyze reactions like proteins, served as the original multitasker. An RNA world in which self-replicating RNA molecules preceded both DNA and proteins could, in principle, get the system started. But no one has demonstrated how the first self-replicating RNA molecule arose, and the chemical pathway from simple molecules to even the most basic RNA sequence remains uncharted. We do not know how life began. We do not know whether it was inevitable, a natural outcome of chemistry, given the right conditions, or whether it was extraordinarily improbable, perhaps the result of a sequence of events so unlikely that it may have occurred only once in the observable universe. Thus, the question that underlies every question in biology remains open. Why? We sleep. Every night, if all goes normally, you lose consciousness for approximately a third of your life. Your muscles go largely limp. Your body temperature drops. Your brain cycles through distinct states of electrical activity that differ dramatically from waking. You become almost entirely unresponsive to the external world, and you experience, in the dream stages, a vivid hallucinated reality generated entirely by your own brain. Sleep is one of the most universal behaviors in the animal kingdom. Every vertebrate studied sleeps, or exhibits something that looks very much like sleep. Even some invertebrates appear to have sleep-like states, and the pressure to sleep is so powerful that sleep deprivation is one of the most effective forms of torture ever devised, producing, within days, hallucinations, cognitive collapse, and eventually death. You would think, given all of this, that we would know with certainty what sleep is for. We do not. There are several compelling partial answers. Sleep appears to play a role in memory consolidation, the process by which experiences are transferred from short-term to long-term storage and integrated into distant knowledge. Studies consistently show that people who sleep after learning perform significantly better on tests of that material than those who remain awake. The sleeping brain appears to be actively processing and organizing the information accumulated during waking hours. Sleep also appears to serve a crucial maintenance function. The glymphatic system, a network of channels in the brain that is far more active during sleep than waking, appears to flush out metabolic waste polluting products, including proteins associated with Alzheimer's disease. The brain, it seems, cleans itself while you sleep. But why sleep evolved in the first place? Why evolution would design an organism to spend a third of its existence in a state of relative helplessness, unable to feed, flee, or fight, remains genuinely unclear. The costs of sleep are enormous from a survival standpoint. Whatever benefits drive its conservation across virtually all animal life must be enormous too we can list candidates. We cannot confidently identify the primary function. The question of what sleep is fundamentally for remains open. How anesthesia works. Every year, hundreds of millions of people undergo surgical procedures under general anesthesia. They are given a drug. They lose consciousness within seconds or minutes. They have no awareness of the hours that follow, and they wake up having experienced, from their subjective perspective, nothing at all. The procedure is so routine, so standardized, so reliably performed by trained professionals, that most patients give it little more thought than any other medical procedure. And Lufsent and Slostes, here is what makes this remarkable. We do not know how it works. We know what anesthetic drugs do at the molecular level. We can describe how they interact with specific receptors and ion channels in nerve cell membranes, membranes. We can identify brain regions whose activity changes under anesthesia. We can characterize the patterns of brain activity that accompany the different depths of anesthetic effect. What we cannot explain is why any of this causes consciousness to disappear. The neuroscience of anesthesia runs directly into the hard problem of consciousness, and the gap is more obvious here than almost anywhere else because the effect is so dramatic and so precisely controllable. A specific molecular intervention removes consciousness entirely and reversibly, and we have no framework that explains as to how a molecular interaction at the level of receptor proteins translates into the presence or absence of subjective experience. Different anesthetic agents work through different molecular mechanisms. Yet, they all produce the same endpoint, the absence of consciousness. This suggests that consciousness depends on something about the overall activity or integration of the brain that all of these agents disrupt, despite their different mechanisms. But what that something is, the neural correlate of consciousness that anesthesia switches off remains unknown. Some of the most prominent theories of consciousness, global workspace theory, integrated information theory, orchestrated objective reduction, make specific predictions about what anesthesia should do to the brain. The experimental evidence is ambiguous. Leifchun Blaken, none of the theories has cleanly won. Every year, more people are anesthetized than in all of human history before modern medicine, and the fundamental reason it works remains a mystery. The placebo effect. A patient is given a sugar pill. They are told it might help their condition. It has no active pharmaceutical ingredient, no mechanism by which it could possibly affect their biology. And yet, in clinical trial after clinical trial, across dozens of medical conditions, a significant proportion of patients given the placebo experienced genuine, measurable improvements. See what it says. Their pain decreases, their symptoms lessen, their bodies change in ways that instruments can detect. The placebo effect is real. It is not imaginary, not merely patients reporting, feeling better to please the researcher. Objective physiological measurements. Blood pressure, cortisol levels, neuroimaging, immune markers, change in ways consistent with therapeutic effect. The body responds to the expectation of treatment, as though treatment has been received. What makes this even stranger is the discovery of open-label placebos. In studies where patients are explicitly told that they are receiving a sugar pill with no active ingredient, that the researcher is not trying to deceive them, that they know exactly what they are taking, a significant proportion still experience improvement. Why? Knowing the pill is inert does not prevent the placebo response. The mind produces therapeutic effects, even when fully aware that the mechanism is belief rather than chemistry. The neurobiological mechanisms of the placebo effect are partially understood. Placebo analgesia, placebo-induced pain reduction, involves the genuine release of endogenous opioids, the brain's own pain-relieving chemicals. When the opioid-blocking drug naloxone is given alongside a placebo, it reduces the placebo's analgesic effect, confirming that real opioid activity is involved. Expectation of relief produces actual relief through actual chemistry. But why? The brain would have evolved this mechanism. The ability to produce genuine therapeutic effects in response to an expectation rather than a treatment is not well understood, nor is the full scope of what the placebo effect can and cannot do, nor is why placebo responses vary so dramatically between individuals and between conditions. The placebo effect is one of the most well-documented phenomena in medicine and one of the least explained. The nature of time feels like the most fundamental feature of existence. Every experience you have is embedded in time. Every thought you think, every sensation you feel, every memory you hold is located at a point in time and separated from other events by intervals of time. The present moment, the now, feels like the most undeniable fact of experience. And the flow of time, the sense of moving from past to future, feels as natural and inevitable as breathing. Physics has almost nothing to say in support of this intuition. Almost everything that physics implies about time is deeply at odds with how we experience it. The laws of physics, at the fundamental level, are time-symmetric. They work equally well run forward or backward. The equations of Newtonian mechanics, of quantum mechanics, of electromagnetism, of general relativity, none of them have a built-in direction. A film of two billiard balls colliding, run in reverse, would be physically valid. The time-symmetric laws of physics have no preferred direction, from past to future. And yet, everywhere in everyday experience, time has an unmistakable direction. Eggs break, but do not unbreak. Coffee cools, but does not spontaneously reheat. The past is fixed and the future is open. This asymmetry, called the arrow of time, requires explanation, and the best available explanation invokes the thermodynamic concept of entropy. The universe started in an extraordinarily ordered slumosum and slormos and pistasis, low entropy state, and has been evolving toward disorder ever since. But this only pushes the question back. Why did the universe start in such an improbably ordered state? No one knows.
Then there is the question of whether time actually flowed, and so
general relativity treats time as a dimension, part of a four-dimensional space-time, in which past, present, and future all exist simultaneously. like positions on a map. The physicist Julian Barbour argued that time does not flow at all, that the sense of duration and change is an artifact of consciousness, not a feature of the physical world. The block universe theory, supported by relativity, suggests that all moments exist equally and that the sense of a moving present is an illusion produced by the mind. Whether time is real, what gives it its direction, and why it appears to flow are questions that physics and philosophy have circled for over a century without resolution. The wow signal. On the evening of August 15th, 1977, a radio telescope at Ohio State University, called the Big Ear, was scanning the sky as part of SETI, the search for extraterrestrial intelligence, when it detected something extraordinary. A signal arrived on a frequency of 1420 megahertz, the frequency of hydrogen, the most abundant element in the universe, and the frequency that scientists had long considered the most logical choice for any civilization attempting to communicate across interstellar space. The signal was narrowband, meaning it was concentrated at a single frequency rather than spread across a range, which is characteristic of artificial transmissions rather than astrophysical, natural astrophysical phenomena. And it was strong, 72 times stronger than the background noise of the sky. Astronomer Jerry Emmon was reviewing the printout when he found it. He circled it in red pen and wrote a single word in the margin: wow. The wow signal, as it became known, has never been detected again. In the 47 years since, the telescope returned to the same region of sky thousands of times. Other facilities have pointed in the same direction. Nothing has been found. The signal appeared for the full 72 seconds that the telescope's beam passed across its source. Its source then was gone. Various explanations have been proposed. A comet passing through the field of view, releasing hydrogen gas, a satellite or Earth-based transmission, atmospheric effects. Each has been examined and found wanting. The comet hypothesis was briefly popular, but has not been confirmed. No known natural or human-made source has been identified that could produce a signal with the wow signal's characteristics at that location. It may have been a one-time transmission from a distant civilization that we happened to catch at exactly the right moment and which has not repeated. It may have been a natural phenomenon we do not yet understand. It may have been a reflection or artifact that we have not correctly identified. Almost half a century later, no explanation has been established. The wow signal remains the most compelling unidentified signal ever detected in the history of SETI, and it remains unexplained. Quantum entanglement. Two particles are created together under the right conditions and then separated. They may travel in opposite directions for miles, or for light years, or, in principle, across any distance. And yet, when you measure a property of one of them, its spin, its polarization, its momentum, the other particle instantly exhibits a correlated property, no matter how far away it is. This is quantum entanglement, and it is one of the most experimentally verified and most conceptually troubling phenomena in all of physics. Einstein hated it. He called it spooky action at a distance and spent considerable effort trying to argue that it could not possibly be what quantum mechanics claimed it was. Surely, he argued, the correlations must be explained by some hidden variables. Some particles of the particles that were set at the moment of their creation, and that determined the measurement outcomes in advance. The particles are like gloves in separate boxes. You don't know which box has the left glove and which has the right until you open one. But there is no mysterious connection. The information was always there. In 1964, physicist John Bell devised a mathematical test that could distinguish between hidden variable explanations and genuine quantum entanglement. The test was run experimentally, most definitively, by Alain Aspect in the 1980s and in increasingly rigorous experiments ever since. The result was unambiguous. Hidden variables do not explain the correlations. The particles genuinely do not have definite properties until measured, and the correlations between them are genuine. They are not explained by pre-existing information. How this works, what the physical mechanism is, by which measuring one particle instantly affects the state of another at an arbitrary distance, remains philosophically unresolved. Nothing in our standard picture of space and time allows for instantaneous action across distances. Yet the correlations are real. They have been used to build quantum cryptography systems. They are a foundation of the emerging field of quantum computing. We use them without understanding them. Quantum mechanics is the most precisely tested theory in the history of science, with predictions verified to more decimal places than any other theory. And we have no idea what it is telling us about the nature of reality. The Cambrian Explosion. For the first 3.5 billion years of life on Earth, the dominant organisms were simple: bacteria, archaea, and single-celled eukaryotes. Life was present. It was widespread, and it was busy transforming the chemistry of the atmosphere and the oceans. But it was not, by any external measure, spectacular. Then, approximately 538 million years ago, something happened that still defies complete explanation. In a geologically brief window of time, perhaps 5 to 25 million years, a blink in the context of the preceding 3 billion. Virtually all of the major body plans that exist in the animal kingdom today appeared in the fossil record simultaneously. Eyes, legs, shells, gills, segmented bodies, nervous systems, jaws, the precursors to every major animal phylum alive today, and many that are now extinct, appear within this single narrow window. This is the Cambrian Explosion, and it is one of the most debated events in the history of life. Darwin himself was troubled by it. The theory of evolution predicts gradual change over long periods of time. The sudden appearance of so many complex body plans, with apparently few transitional forms in the preceding record, looked disturbingly abrupt. Darwin hoped that future fossil discoveries would fill in the record. They have helped, but the basic pattern, a concentrated burst of diversification unlike anything before or since, has only become more clearly defined. As the fossil record has improved, proposed explanations involve combinations of factors. Rising oxygen levels enabling more complex metabolisms, ecological interactions driving rapid arms, races between predators and prey, changes in ocean chemistry, genetic innovations enabling greater developmental flexibility. The discovery of the Hox genes, master regulatory genes that control the basic body plan of all animals, suggested that once the genetic toolkit for building complex bodies existed, variation could proceed rapidly. None of these explanations is fully satisfying on its own, and the interactions between them are poorly understood. Why the explosion happened when it did, why it happened so fast, and why nothing comparable has happened in the 500 million years since remain open. Questions. Why? We dream every night. During the phases of sleep, characterized by rapid eye movement, your brain generates an experience that is in many ways indistinguishable from waking reality. You inhabit spaces. You interact with people. You feel emotions, sometimes mundane, sometimes overwhelming. You are convinced while it is happening that what you are experiencing is real. And then you wake up and the constructed world dissolves and you are left with fragments that fade within minutes. Dreams are one of the most universal human experiences and one of the least understood. Every culture in history has had theories about them. Most ancient cultures interpreted them as messages from gods, ancestors, or the unconscious forces of the universe. Freud interpreted them as expressions of repressed desires. Neurologists have proposed that they are simply the byproduct of memory, consolidation, meaningless noise, generated by a brain tidying its files. Others argue they serve an emotional regulation function, allowing the brain to process difficult experiences in a context decoupled from real-world consequences. The honest scientific answer is that we do not know why we dream, or whether dreams serve any function at all. What we know is that dreaming occurs primarily during REM sleep, that the brain during REM is nearly as active as during waking, and that the regions responsible for critical evaluation and self-awareness show reduced activity, while the emotion-generating and memory-activating regions show elevated activity. This is why dreams feel real and emotionally vivid, but are rarely critically examined by the dreamer. We know that REM sleep is conserved across mammals and most birds, which suggests it serves some important function because evolution ruthlessly eliminates what is not useful. But yes, sleep researchers debate whether dreaming itself is the function or merely a side effect to whatever REM sleep is actually doing to the brain. Some of the most vivid and creative mental experiences you will have in your entire life occur in dreams. Where they come from and what they mean, or whether they mean anything, remains one of the oldest unanswered questions in the history of human inquiry. The fine-tuned universe, the fundamental constants of physics, the strength of gravity, the strength of the electromagnetic force, the masses of elementary particles, the cosmological constant, have specific numerical values. These values are not derived from any deeper theory. They are measured, and as far as we know, they could have been different. What physicists have discovered over the course of decades of careful analysis is that if these constants were even slightly different, the universe would be radically inhospitable to anything we recognize as complexity. If gravity were slightly stronger, stars would burn out in thousands of years rather than billions, leaving no time for planets to form or life to evolve. If the electromagnetic force were slightly weaker, atoms would not hold together. If the cosmological constant were even slightly larger, the universe would have expanded so rapidly after the Big Bang that matter could never have clumped together to form galaxies. The degree of precision required is startling. The cosmological constant, for instance, appears to be fine-tuned to within 1 part in 10 to the power of 120, a number so close to zero that it strains intuition. Had it been even fractional larger, we would not be here to observe it. This is the fine-tuning problem, and admits several radically different kinds of responses. The theological response argues that the universe was designed by an intelligence that set the constants to permit life. The anthropic response argues that the apparent fine-tuning requires no explanation beyond the selection effect. We can only observe universes compatible with observers. So, of course, the universe we observe has parameters compatible with observers. The multiverse response argues that there are an enormous or infinite number of universes with different constants, and we happen to inhabit one where life is possible. Each response has serious problems. None is broadly accepted. The fine-tuning of the physical constants of the universe is a genuine scientific puzzle, and the best we can honestly say is that we do not know whether it requires an explanation, and if it does, what that explanation might be. Ball lightning. The accounts span centuries and come from every continent and culture. A sphere of glowing light, typically between the size of a golf ball and the size of a basketball, appearing during or after thunderstorms, moving slowly through the air, or hovering in place, sometimes entering buildings through windows or even closed glass, persisting for several seconds to several minutes, and then disappearing silently or with a loud bang. Ball lightning is one of the most widely reported and most thoroughly unresolved phenomena in atmospheric science. The existence of ball lightning is not seriously disputed. There are thousands of credible eyewitness accounts spanning hundreds of years. Hundreds of years. Multiple accounts must come from trained scientists, pilots, and military personnel. A small number of photographs and at least one video purportedly show the phenomenon. In 2014, a team of Chinese researchers who were conducting unrelated spectroscopic measurements of normal lightning inadvertently recorded what appears to be ball lightning, producing the first scientifically documented measurement of its spectrum. What produces it is entirely unknown. More than 200 hypotheses have been proposed over the last century. Microwave radiation, trapped in a plasma bubble, oxidizing silicon nanoparticles, combustion of atmospheric gases, vortex rings of plasma, hallucinations induced by electromagnetic fields affecting the brain, rare atmospheric electrical effects, Each hypothesis explains some reported features and fails to account for others. The phenomenon passes through glass. It appears inside aircraft and submarines. It sometimes appears in clear weather with no lightning. It produces a variety of colors and behaviors that no single proposed mechanism easily accommodates. Ball lightning has been observed for centuries and remains entirely unexplained. In a scientific era that has explained the behavior of subatomic particles and the formation of galaxies, a glowing sphere of light floating through the air for a few seconds remains beyond our understanding. The Riemann Hypothesis. In 1859, a German mathematician named Bernhard Riemann published a paper on the distribution of prime numbers that contained, almost as an aside, a hypothesis that has haunted mathematics ever since. It is the most famous unsolved problem in mathematics. Its proof, or disproof, would reshape number theory, cryptography, physics, and our fundamental understanding of the structure of the integers. Prime numbers are the atoms of arithmetic. Every positive integer can be expressed uniquely as a product of primes. They are irregularly distributed among the integers, unpredictably scattered, with no obvious pattern in where each one falls. And yet, on a large scale, their distribution follows a statistical regularity. Described by the prime number theorem, they become gradually less dense as numbers grow larger, in a way that can be precisely characterized. Riemann discovered a deep connection between the distribution of prime numbers and the behavior of a particular mathematical function called the Schoenchen Riemann zeta function. This function can be evaluated for complex numbers that combine real and imaginary components, and it has points called zeros where its value is exactly zero. Riemann calculated the first few of these zeros and noticed something striking. They all appeared to lie on a single vertical line in the complex plane, the line where the real component of the input equals 1/2. His hypothesis: all non-trivial zeros of the Riemann zeta function lie on this line. If true, it would imply deep regularities in the distribution of prime numbers and connect to fundamental structures in mathematics and physics. If false, it would imply that the distribution of primes has irregularities beyond what current theory suggests. Bosch-Simpson suggests more than 10 trillion zeros have been computed, and everyone lies on the critical line. But a proof, or a counterexample, has eluded every mathematician who has attempted it in the 165 years since Riemann's paper. The hypothesis sits at the intersection of number theory, complex analysis, and physics, and its resolution would be one of the greatest achievements in the history of mathematics. The Fermi Paradox revisited. We have explored this paradox before in these sessions, but it bears returning to, because the more deeply you examine it, the stranger it becomes. The universe is 13.8 billion years old. It contains at minimum 2 trillion galaxies, each with hundreds of billions of stars. Rocky planets in habitable zones are common. The chemistry of life's building blocks is apparently widespread. Amino acids, nucleobases, and organic molecules have been detected in meteorites, in interstellar clouds, and in the atmospheres of distant worlds. Given these numbers, the statistical expectation for intelligent life in the universe is not one's civilization. It is an enormous number of civilizations, spread across billions of years. Some of them should be millions of years more advanced than we are. Some should have had time to colonize entire galaxies. Some should be transcenders, signals that we could detect. The technology, we have detected nothing, heard nothing, found no megastructures, no engineered stars, no interstellar transmissions, no signatures of industry visible from the galaxies of galaxies. The universe, which statistically should be crowded with intelligent life, is silent. The proposed solutions to this silence have become darker and more specific as science has advanced. The Great Filter Hypothesis suggests that somewhere in the developmental path, from simple chemistry to interstellar civilization, there is a step so difficult that almost no civilization survives it. The question is whether that filter is behind us, in which case we are extraordinarily lucky survivors, or ahead, in which case our civilization faces a challenge that almost no civilization before us has overcome. The rare Earth hypothesis argues that the conditions required for complex life are so specific that intelligent life may be vanishingly rare. Despite the size of the universe, the dark forest hypothesis argues that the silence is itself a survival strategy, that all advanced civilizations learn to hide because the universe is a predatory environment. What the silence actually means, whether it is evidence of our uniqueness, our danger, or our fundamental misunderstanding of something, remains completely unresolved. And the more carefully we listen, the more complete the silence becomes. How the brain stores memory. You remember your first day of school. You remember the face of someone you love. You remember the words to a song you have not heard in 20 years. You remember how to ride a bicycle, how to swim, how to write your own name. These memories span decades, survive sleep and illness and distraction, and are accessible with varying reliability on demand. How the brain accomplishes this is one of the most intensively studied and most incompletely understood questions in all of neuroscience. The leading hypothesis for the physical basis of memory involves long-term potentiation, the strengthening of synaptic connections between neurons that fire together repeatedly. The idea, summarized by the neuroscientist Donald Hebb, is that neurons that fire together wire together. Every time two neurons activate in closer succession, the connection between them is strengthened. And over time, with repeated activation, this strengthening becomes persistent. A physical trace of the experience that can be reactivated. But this account leaves many questions unanswered. How do memories survive the constant turnover of proteins in synaptic connections? The proteins that constitute synapses have lifetimes of days to weeks. Yet memories can last decades. Something must be ensuring that the pattern is maintained across this constant molecular replacement. What that mechanism is remains unclear. Fundamentally, neuroscience has not identified where in the brain specific memories are stored. Early research suggested that memories might be localized, stored in specific cells or groups of cells. But subsequent work has suggested that memories are more distributed, encoded in patterns of connectivity across large networks. The engram, the physical trace of a specific memory, has been the subject of experimental search since the 1920s and remains elusive. Every waking moment, your brain is recording and retrieving information with an efficiency and capacity that no human-built technology has approached. We do not know how. Why music moved us. Music is universal. Every human culture that has ever been studied has music. Music appears in the archaeological record tens of thousands of years ago. The brain dedicates substantial neural resources to processing it, and for most people, music produces some of the most powerful emotional experiences of their lives. Chills along the spine, tears arising without sadness, the sensation of being transported, moved literally and emotionally by organized patterns of sound. No other purely sensory experience has this effect with such reliable power, and science has no satisfying explanation for why. The emotional responses to music are not simply learned associations, not just the result of connecting particular songs with personal memories, though that mechanism is certainly real and potent. Music produced in unfamiliar cultural traditions can still be emotionally effective. Certain musical structures, rising melodic tension, sudden harmonic resolution, the anticipation and fulfillment of rhythmic patterns, produce emotional responses in listeners with no prior exposure to those structures. Neuroimaging studies show that music activates the same reward circuits as food, sex, and other biologically significant stimuli. Dopamine is released in the nucleus accumbens, a region associated with pleasure and motivation. The physical sensation of musical chills is measurable. Heart rate changes, skin conductance changes, goosebumps. Music produces genuine physiological responses through mechanisms that overlap with those serving survival-critical rewards. But why? What evolutionary purpose is served by the ability of organized sound to produce intense emotional experiences? Proposed explanations invoke social bonding, emotional communication, mother-infant attachment, sexual selection, and the byproduct theory. The idea that music is a happy accident, exploiting neural mechanisms that evolved for other purposes. None of these fully accounts for the specificity of the response or the universality of the experience. Music moves us. We have no idea why. The mystery of aging. Every organism with a body ages. Cells accumulate damage. Tissues lose their ability to repair and regenerate. Systems that worked reliably for decades begin to fail. And, eventually, the accumulated dysfunction becomes incompatible with continued life. This seems inevitable. The simple consequence of wear and tear on biological machinery operating for decades. In a world full of radiation, oxidative stress, and random molecular errors. But the biology of aging is considerably stranger than this intuitive picture suggests. And The questions of why organisms age at all, why evolution did not produce organisms capable of indefinite maintenance and repair, is genuinely open. Different species have radically different lifespans that do not scale simply with body size or metabolic rate. The Greenland shark lives for approximately 400 years, reaching sexual maturity around 150. The naked mole rat, a small sodent, lives for 30 years, 10 times longer than other rodents of comparable size, and shows almost no age-related increase in mortality rate throughout its life. The bowhead whale lives for 200 years. Some trees are thousands of years old. The hydra, a tiny freshwater invertebrate, appears not to age at all. These examples demonstrate that there is no physical necessity to aging. Evolution has produced radically different rates of senescence in different lineages. The question is, what determines those rates and whether the mechanisms could be altered? Several theories of aging have strong experimental support. The accumulation of senescent cells that have stopped dividing but continue to secrete inflammatory signals, appears to be a major driver of age-related dysfunction. Telomere shortening limits the number of times cells can divide. Mitochondrial dysfunction accumulates over decades. Epigenetic changes alter gene expression in ways that may be reversible. Recent experiments have extended the healthy lifespan of various animals through genetic and pharmacological interventions. Life found out whether the underlying mechanisms of human aging can be understood and altered well enough to substantially extend. The human health span remains one of the most consequential open questions in biology. Déjà vu. You are in a place you have never been before, or you are having a conversation you have never had before, and yet an overwhelming certainty washes over you that you have been here, have had this exact conversation, have experienced this precise sequence of events before. The certainty feels completely real, and then within seconds it fades, and you are left with nothing but the strange residue of an experience you cannot account for. Déjà vu is one of the most widely reported anomalous experiences in human psychology, affecting an estimated 60 to 70% of people at some point in their lives, and one of the most poorly understood. The name is French for already seen, but the experience extends beyond vision to encompass the full sense, the sense that this moment has been lived before. Part of what makes déjà vu difficult to study scientifically is that it is brief, unpredictable, and impossible to induce reliably in laboratory conditions. Researchers must rely on self-report, and self-report of an experience defined partly by its sense of unreality is inherently tricky. The most widely accepted neurological explanation proposes a mismatch between two memory systems. One system is responsible for the familiarity signal, the sim or si. Nace, the feeling of recognition that normally accompanies truly familiar things. Under normal circumstances, this signal fires in response to things you have actually encountered before. In déjà vu, the hypothesis goes, this familiarity system fires briefly and inappropriately in response to something new, creating the subjective experience of recognitions without any actual memory to support it. Some support for this comes from epilepsy research. Patients with temporal lobe epilepsy, whose seizures originate in the brain regions associated with memory and familiarity, often experience prolonged and intense déjà vu as a seizure aura. Electrical stimulation of certain temporal lobe structures during brain surgeries has also produced déjà vu in conscious patients. This localization suggests this experience has a specific neural substrate, but why the familiarity system misfires in otherwise healthy people, what triggers it, and whether the experience has any relationship to actual prior experiences, whether some fragment of a real memory is involved, Laurel, remain unanswered. Déjà vu is common enough that almost everyone has felt it, and rare enough that its mechanisms have never been definitively established. The Mpemba Effect here is a claim that sounds obviously wrong. Hot water can, under certain circumstances, freeze faster than cold water if you fill two identical containers, one with hot water, one with cold water, and place them in a freezer at the same time. The hot water will sometimes freeze first. This seems to violate basic thermodynamics. Cold water is already closer to the freezing point. It should have less temperature to lose. It should freeze faster. And in many experiments, it does. But in some experiments, under some conditions, the hot water wins. And explaining why has proved to be one of the most contentious minor puzzles in physics. The effect is named for Erasto Mpemba, a Tanzanian student who noticed in 1963 that hot ice cream mix placed in a freezer froze faster than cold mix. He brought this observation to his physics teacher, who dismissed it. He later raised it with a visiting professor, Dennis Osborne, who took it seriously enough to investigate. Mpemba and Osborne published a paper on the effect in 1969, and their names have been attached to it ever since. Proposed explanations for the Mpemba effect are numerous and contradictory. Hot water evaporates as it cools, leaving less water to freeze. But this effect seems too small to explain the phenomenon in all cases. Hot water may have less dissolved gas, altering its thermal properties. Temperature gradients in the hot water may drive convection that accelerates cooling. The properties of hydrogen bonds in water change with temperature in ways that may affect the dynamics of freezing. The problem is that the Mpemba effect is highly inconsistent. Small changes in container geometry, water source, freezer temperature, and other variables can eliminate the effect or reverse it. Some careful experimental studies have failed to reproduce it at all. Others have found it reliably under specific conditions. In 2020, researchers proposed an explanation based on the behavior of hydrogen bonds in water, suggesting that in hot water, these bonds store energy in a specific way that is released during cooling, accelerating the process. The proposal is interesting, but not universally accepted. A phenomenon that seems impossible, that has been observed repeatedly, that has been studied for 60 years, and that still has no agreed explanation. The Mpemba Effect is one of science's most accessible and most persistent small mysteries. animal consciousness. When your dog greets you at the door, its tail wagging, its body radiating what appears to be joy, is there something it is like to be your dog? Is there an inner experience, a felt quality of pleasure and recognition accompanying those behaviors? Or is it an extraordinarily sophisticated biological machine, producing the outward signs of emotion without any inner experience of them? The question of animal consciousness is not peripheral to the study of mind. It is central, and it is one that science has conspicuously struggled to answer. The Cambridge Declaration on Consciousness, signed in 2012 by a prominent group of neuroscientists, stated that non-human animals possess neurological substrates that generate consciousness, that the evidence for conscious experience is not limited to humans. The neural structures associated with conscious states in humans, the cortex, the thalamus, the limbic system, are present in other mammals and in many other vertebrates, though in different forms and proportions. Certain behaviors are suggestive of inner experience. Elephants appear to grieve their dead. Chimpanzees pass the mirror self-recognition test, suggesting some form of self-awareness. Crows appear to plan for the future, hiding food in locations they will return to days later. Octopuses, with nervous systems organized very differently from vertebrates, show problem-solving, play behavior, and what appears to be individual personality. But behavior, however suggestive, cannot prove the presence of inner experience over Mpemba. But awesome, the philosophical zombie, a being that behaves exactly like a conscious creature but has no inner experience, is at least conceptually possible. We cannot, from the outside, determine whether another entity has inner experience or merely produces its behavioral correlates. The question matters enormously for ethics, for how we treat the billions of animals in human care and in the wild. And it matters for understanding consciousness itself, whether it is uniquely human, whether it is widespread in nature, whether it exists in forms radically different from our own. We genuinely do not know. The origin of language. Every human child, given normal developmental conditions, acquires language, not just the ability to communicate. Many animals communicate, but the ability to generate and understand an effectively infinite number of novel sentences using a finite set of words and grammatical rules. Language with recursive structure, with displacement, the ability to talk about things absent in time and space, with the capacity to describe abstract concepts, hypothetical scenarios, and the inner states of other minds. No other species has developed anything remotely comparable. The calls of whales, the dances of bees, the signing of great apes trained in human sign language. All of these are impressive, and all of them are categorically different from human language in structure, in generativity, and in what they can express. How human language evolved is one of the most contested questions in cognitive science, linguistics, and evolutionary biology. The difficulty is that language leaves almost no direct fossil record. Soft tissue does not preserve. We can infer from skull morphology something about the brain structures present in our ancestors. We can look at the anatomy of the vocal tract. We can examine the archaeological record for behavioral evidence of symbolic thinking, cave paintings, personal ornaments, deliberate burial that might indicate language-capable minds. The linguist Noam Chomsky famously argued that language is a uniquely human capacity made possible by specific cognitive adaptation, a language acquisition device wired into the brain that has no precursor in other species. Others argue that language emerged gradually from more general cognitive abilities, enhanced memory, more sophisticated social cognition, greater capacity for imitation and intentional communication, that were themselves built incrementally through evolution. The deepest puzzle is perhaps the most basic. How did the first word come to mean anything? The meaning of a word is a social convention. It works because a community agrees to use it in a particular way. But how does the first word in a language get established before there is a community of speakers to agree on conventions? The origin of meaning of the relationship between sound and reference is a philosophical problem that has not been solved. Turbulence. Fill a glass of water and stir it vigorously. Watch what happens as the motion dies down. The swirling eddies forming within eddies, the chaotic, unpredictable patterns of water in motion. The way the energy of your initial stir cascades down through larger and smaller scales, until it dissipates as heat. What you are watching is turbulence, and it is one of the most computationally intractable problems in all of physics. The equations that govern the motion of fluids, the Navier-Stokes equations, have been known since the 19th century. They are deterministic, given the state of a fluid. At one moment, the equations in principle determine its state at all subsequent moments. The problem is solving them in the turbulent regime. When fluids move fast or are sufficiently disturbed, the solutions become extraordinarily complex, sensitive to initial conditions, and practically impossible to compute exactly. Turbulence affects virtually everything in the technological world: aircraft design, pipeline flow, weather prediction, the behavior of blood in the cardiovascular system, the mixing of fuel in combustion engines, the circulation of the atmosphere and oceans. Engineers have developed empirical models and approximations that work reasonably well in practice, but a fundamental theoretical understanding of turbulence, one that derives its properties from first principles rather than empirical fitting, also does not exist. The Clay Mathematics Institute has identified 6 unsolved Millennium Prize problems. Mathematical problems whose solutions would be of such fundamental importance that $1 million prize awaits the solver of each. One of them is directly related to the Navier-Stokes equations, proving whether smooth solutions always exist, or whether singularities, points where the mathematics breaks down, proving, can develop in finite time. The problem of turbulence has been called the last great unsolved problem of classical physics. Richard Feynman, one of the greatest physicists of the 20th century, described it as the most important unsolved problem of classical physics. Fissot. Away. Decades after Feynman's observation, it remains unsolved, and the turbulent flow of every river, every weather system, every commercial flight through the atmosphere continues to be a computational and theoretical challenge that our most powerful tools have not mastered. Near-death experiences. Patients resuscitated after cardiac arrest sometimes report experiences that challenge standard neuroscientific assumptions about the relationship between brain activity and consciousness. They describe a sense of leaving their body and observing the resuscitation from above. They describe moving through a tunnel toward light. They describe encounters with deceased relatives, a sense of profound peace, and in some cases, the experience of a life review in which the events of life were simultaneously present. Near-death experiences are not rare. Ophthalmos. Studies suggest that between 10 and 20% of cardiac arrest survivors report some form of near-death experience. The experiences are reported across cultures and centuries with notable similarities in core features, while specific content varies with cultural background. What makes these experiences scientifically challenging is that they are reported from periods when, by clinical measures, brain activity has been severely compromised or absent. Cardiac arrest produces loss of consciousness within seconds, and the brain's electrical activity, measurable by EEG, flatlines. Standard neuroscience assumes that conscious experience requires active brain function. If patients are having experiences during periods of minimal or absent measurable brain activity, this assumption is challenged. Skeptical explanations include the release of endogenous compounds like DMT during physiological stress, the activation of residual brain activity during the period before complete cessation or after the initiation of resuscitation, the construction of false memories about the experience after return to consciousness, and the cultural molding of inherently confused physiological states into narratives familiar from prior knowledge about near-death experiences. Researchers have attempted to test the out-of-body component directly by placing objects visible only from above in resuscitation rooms to see whether patients can report what they saw. Results have been inclusiveness, not because evidence of veridical perception has been found, but because of methodological difficulties. The phenomenon remains neither confirmed nor debunked, and its explanation within standard neuroscience remains contested. The size of the universe, the observable universe, the portion of the universe from which light has had time to reach us in the 8 billion years since the Big Bang, has a radius of approximately 46 billion light-years. It contains an estimated 2 trillion galaxies, each containing hundreds of billions to trillions of stars. The scale is so far beyond ordinary human intuition that the numbers are essentially meaningless at the level of direct experience. But the observable universe is not the universe. It is the portion of the universe we can see. Beyond the edge of the observable universe, the universe continues, and we have no direct information about how far it extends or whether it extends infinitely. Current cosmological models, based on the measured properties of the universe, suggests that the total universe is vastly larger than the observable portion, possibly by an enormous factor. Some inflationary models predict that the universe is effectively infinite. Others predict a very large but finite size. We have no observational access to the regions beyond our cosmic horizon, and no current technology or theory offers any path to obtaining it. This creates a profound philosophical problem. If the universe is infinite, then, by straightforward probabilistic reasoning, every possible arrangement of matter that can exist must exist somewhere, including exact duplicates of you, reading these exact words in identical solar systems, in identical galaxies, not metaphorically similar, but physically identical. Particle for particle, you would have an infinite number of exact copies at sufficiently large distances. The physicist Max Tegmark has calculated the distance to your nearest statistical doppelganger based on the number of possible quantum states within a human-sized volume of space. The number is almost incomprehensibly large, on the order of 10 to the power of 28 meters. But if the universe is infinite, the distance, however large, is finite. The copy exists. Somewhere, out beyond any distance light could ever travel, there is someone who is you, having an experience indistinguishable from this one. Whether this is a meaningful claim about reality, or simply an artifact of the mathematics of infinity, is a question that cannot currently be resolved. The size and structure of the universe beyond what we can observe is, and may remain, completely unknown. Why? We laugh. Something strikes you as funny. Before you have consciously decided to respond, before you have formed any intention, your respiratory system begins a rapid series of involuntary contractions. Your facial muscles engage in a specific and largely uncontrollable configuration, and you produce a vocalization. Sometimes quiet, sometimes explosive, that signals to everyone around you that something has happened in your mind that your body could not contain. Laughter is one of the most distinctively social of all human behaviors. It is contagious in precisely the way emotions are contagious. Hearing laughter makes you more likely to laugh, even without knowing its cause. It is used more to cement social bonds than to express genuine amusement. Most laughter in social situations occurs in response to ordinary conversational exchanges rather than to anything, particularly if funny. And the question of what is funny, what triggers laughter, why the brain responds to it, with what appears to be genuine reward, has occupied philosophers and scientists for centuries without resolution. The most durable theory of humor is the incongruity theory, the idea that humor arises when two incompatible frames or expectations are brought together in a way that resolves unexpectedly. The punchline of a joke works by setting up an expectation and then violating it in a way that is surprising, but, in retrospect, makes a kind of sense. The brain, confronted with an incongruity it can resolve, produces laughter as a signal to itself and others that the apparent problem is benign. This explains something about the structure of humor, but not why The resolution of incongruity should produce anything, like the physical experience of laughter, or why that physical experience should be pleasurable, or why it should be contagious. The evolutionary function of humor and laughter is genuinely contested. Proposed functions include social bonding, the signaling of playfulness and non-aggression, and the exercise of cognitive flexibility. What we can say is that laughter is ancient. Great apes laugh in ways structurally similar to human laughter during play and tickling. That it is deeply social, and that, whatever it is for, the human capacity to find things funny and to broadcast that finding to the world around us is one of the most distinctive and most pleasurable features of being the kind of creature we are. Mathematical truth. Mathematics is unreasonably effective at describing physical reality. This phrase, in various forms, has been attributed to physicist Eugene Wigner, who noted in a 1960 essay the extraordinary coincidence, if it is a coincidence, between the structures discovered by pure mathematicians working with no thought of application, and the structures that later turn out to describe the physical world with perfect precision. Non-Euclidean geometry developed in the 19th century as a purely abstract exercise in what happens when you drop one of Euclid's axioms turned out to be exactly the geometry required by Einstein's general relativity to describe the curvature of space-time. The mathematics of group theory developed to understand abstract algebraic structures, turned out to be the language of particle physics. Complex numbers, imaginary numbers involving the square root of -1, dismissed for centuries as mathematical fictions, are fundamental to quantum mechanics. Why should the structures discovered by mathematicians following purely internal, aesthetic, and logical criteria map so precisely onto the architecture of the physical universe? This question has no agreed answer. One response is the multiverse answer. In a universe with enough variety, some corner of it will have physical laws that match the structures mathematics discovers. We happen to be in that corner. Another response is the selection effect. The physical world does have structure, and mathematics is, at bottom, the study of structure, so some alignment is inevitable. A third response is the Platonic one. Mathematical objects are real in some deep sense, and the physical universe is, at bottom, mathematical. So the alignment is not a coincidence, but a feature of reality itself. Physicist Max Tegmark has proposed the mathematical universe hypothesis, the idea that the physical universe is not merely described by mathematics, but is a mathematical structure. All self-consistent mathematical structures exist physically. Somewhere in the multiverse, we inhabit one of them. This is a proposal so extreme that it is difficult to distinguish from fantasy, and yet it follows with some logical force from the premises of the argument. Why mathematics works is one of the deepest questions about the relationship between mind and reality, and it has no answer. The migratory navigation of animals. Every year, the Arctic tern makes a round trip of approximately 70,000 kilometers from its Arctic breeding grounds to the Antarctic and back. Every year, monarch butterflies in North America make a journey of up to 5,000 kilometers from Canada and the United States to specific overwintering sites in the mountains of central Mexico, sites that no individual butterfly has ever visited before, reached by a navigation system encoded in the butterfly's genes rather than learned from experience. Every year, sea turtles return to the exact beach where they were born to lay their eggs, navigating across thousands of kilometers of open ocean with a precision that exceeds the capabilities of most human navigational instruments. Fleischmer, migratory birds cross entire continents and oceans at night, guided by stars, by landmarks, and by something else, slus. Something else, something that allows them to navigate even on overcast nights when no stars are visible. That something is magnetoreception. Say, the ability to sense the Earth's magnetic field and use it as a navigational compass. Magnetoreception has been demonstrated in birds, fish, sea turtles, honeybees, and other animals. What remains largely unknown is how it works at the biological level. The leading hypothesis involves tiny crystals of magnetite, a magnetic mineral found in the beaks of birds and in other animals, which might function as biological compass needles. Another hypothesis, supported by experimental evidence, involves quantum mechanical effects in certain proteins. In the eyes of birds, cryptochrome molecules that undergo chemical reactions sensitive to magnetic field orientation when struck by light, effectively allowing birds to see magnetic field lines superimposed on their visual field. Both mechanisms may be real. Both are poorly understood. The fact that a butterfly hatching from a chrysalis in Ontario possesses a navigational system accurate enough to carry it to a specific forest in Mexico that its great-great-grandparents visited without any instruction, any map, any learning, is one of the most extraordinary facts in all of biology. How it works in the detail of molecular biology and quantum physics remains one of the most fascinating open questions in the study of animal behavior, the Fermat primes and mathematical patterns. Here is a sequence of numbers: 3, 5, 17, 257, 65,537. These are the known Fermat primes, prime numbers of the form 2 to the power of 2 to the power of n plus 1. Fermat believed, in the 17th century, that all numbers of this form were prime. The first 5 are, and then the pattern breaks, completely and irreversibly. The 6th Fermat number, 2 to the power of 32 plus 1, was shown by Euler to be divisible by 641. It is not prime, and as far as mathematicians have been able to determine by calculation extending to truly astronomical ranges, no Mpemba Fermi prime exists beyond the 5 that Fermat originally computed. This is a small example of a much larger phenomenon. Mathematics is full of patterns that appear to hold, that hold for every case that can be computed, and that then either prove to hold always, sometimes requiring centuries of work to establish, or that turn out to fail, sometimes spectacularly, at some unfathomable distance along the number line. The Goldbach conjecture, proposed in 1742, states that every even integer greater than 2 is the sum of 2 prime numbers. Every even number that has ever been tested satisfies this. Calculations have extended to numbers so large that printing them would require the document longer than this script. There is no known counterexample. There is also no proof. The relationship between mathematical truth and mathematical provability is itself a source of deep mystery. Gödel's incompleteness theorems established that any sufficiently powerful formal system contains true statements that cannot be proved within that system. There are mathematical truths that are simply out of reach of formal proof, no matter how sophisticated the mathematical machinery brought to bear on them. This implies that the landscape of mathematical truth, SPO, is larger than the landscape of mathematical knowledge. That there are things that are true that we can never prove are true. The boundary between the knowable and the unknowable in mathematics is not a limitation of our intelligence or our tools. It is a structural feature of mathematics itself. The taste of water. You have tasted water your entire life. And for most of that life, you have probably taken it for granted that water tastes like water, that its flavor, or rather its apparent lack of flavor, is simply the neutral baseline against which all other tastes are measured. This intuition turns out to be wrong in an interesting way. Water does not simply taste like nothing. When you drink water after eating something salty or sweet or bitter, it acquires a distinct taste. Sometimes slightly sweet, sometimes slightly sour. The perception of water's taste is context-dependent, shaped by what your taste receptors have recently encountered. For a long time, mainstream taste science held that mammals could not actually taste water, that the perception of water was entirely a matter of texture and temperature rather than a distinct sensory quality. Then, in 2017, a study published in Nature Neuroscience identified a specific population of taste cells in the mouths of mice that respond to water. Not to the chemicals dissolved in water, but to water itself. These cells appear to be the same cells involved in detecting sour tastes, and they may function as part of a system for monitoring hydration. What waters tastes like to a mouse and whether anything analogous occurs in humans remains under investigation. But the basic finding that there may be a dedicated sensory apparatus for detecting water and that water has a taste in some meaningful neurological sense is counterintuitive and fascinating. The sense of taste, which feels so immediate and so obvious, turns out to be considerably stranger than it appears. The 5 basic tastes, sweet, salty, sour, bitter, and umami, may be joined by others, including fat taste, starchy taste, and now possibly water taste. The biology of how the brain constructs the experience of flavor from chemical signals on the tongue, combined with olfactory input, temperature, texture, and context, is a rich area of ongoing research where basic questions remain unanswered. Gravity at the quantum scale. Gravity is the force you experience most directly and most constantly. It holds you to the surface of the Earth holds the Earth in orbit around the Sun, holds galaxies come together, and governs the large-scale structure of the universe, of the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is the one you can most easily demonstrate with a dropped object. It is also the only one that has resisted every attempt at a quantum description. And this resistance is not a minor technical problem. It is a fundamental compatibility that lies at the heart of the most significant unresolved tension in all of physics. The other three forces have been successively described by quantum field theory, a framework in which forces are transmitted by particles, in which quantum uncertainty and superposition are built into the foundation, and which has produced predictions verified to extraordinary precision. The standard model of particle physics, which describes these three forces and the particles they act on, is the most experimentally successful theory in the history of science. General relativity, Einstein's theory of gravity, is equally successful in its domain. It describes gravity as the curvature of space-time produced by mass and energy, and its predictions have been verified in everything, from the bending of light by the sun to the detection of gravitational waves from colliding black holes. It is, by any measure, a magnificent theory. The problem is that they are incompatible at the scale of everyday life and most astrophysics. This incompatibility does not matter. The two theories can be applied separately in their respective domains. But at extreme conditions, inside black holes, at the moment of the Big Bang, both theories are simultaneously relevant, and they produce contradictions. Space-time becomes infinitely curved at singularities. Quantum mechanics says infinite values are unphysical. Something must give. We do not know what. String theory, loop quantum gravity, and other frameworks have been proposed as paths to unification. None has produced experimentally testable predictions that have been confirmed. The unification of gravity and quantum mechanics, the theory of quantum gravity, remains the great outstanding problem of theoretical physics. It has been the goal of many of the most brilliant physicists alive for the last half-century. It has not been achieved. The Yanny-Laurel problem and perceptual disagreement. In 2018, an audio clip circulated online that produced one of the most dramatic demonstrations of perceptual disagreement in recent memory. Some listeners heard the clip as clearly saying the name Laurel. Others, hearing the exact same audio file, heard the name Yanny just as clearly. Both groups were convinced that what they heard was the only reasonable interpretation of the sound. Both were correct in the sense that the acoustic signal genuinely contained elements that could support either interpretation. This episode was a public demonstration of something that perceptual scientists have studied for decades. The degree to which perception is not a passive recording of external reality, but an active construction shaped by priors, experience, expectation, and the specific filtering characteristics of individual perceptual systems. The Yanny-Laurel clip is ambiguous because it contains acoustic energy at multiple frequencies that happen to coincide with the characteristic features of both words. Your auditory system, shaped by a lifetime of experience, with the sounds most common in your environment, applies a prior that biases the interpretation. People who more easily hear high-frequency sounds tend to hear Yanny. Those more sensitive to lower frequencies tend to hear Laurel. Age, hearing history, and the device you play it on all influence which interpretation wins. What the Yanny-Laurel phenomenon illustrates, and what remains genuinely mysterious at the deepest level, is the relationship between the physical signal, the physical signal, and the perceptual experience. Two peoples receiving the same sensory input construct different perceptual worlds from it. Neither perception is wrong. Both are constructed. The experience of a sound, a color, a face. The felt quality of any percept is not a direct readout of the external world. It is a model generated by the brain that usually corresponds well to the world, but that can diverge from it in ways that reveal the constructedness of every experience. The hard problem of consciousness reappears here. Not only do we not know why experience exists, we do not know why two people with different perceptual histories construct different experiences from the same input. And more fundamentally, we do not know how any physical process in the brain produces any experience at all. Perception science can map the computations involved in enormous detail. What it cannot explain is why those computations feel like anything. The Oklo natural nuclear reactor. In 1972, scientists analyzing uranium ore from a mine in Oklo, Gabon in Central Africa, made a startling discovery. The ore had an anomalously low concentration of uranium-235, the isotope used in nuclear reactors and weapons. Some of the uranium-235 had been consumed as if it had been used as fuel. Investigation revealed the extraordinary truth. Approximately 2 billion years ago, a natural nuclear chain reaction had spontaneously started and sustained itself for hundreds of thousands of years in a uranium deposit in what is now Gabon. The Oklo mine contains the remnants of the world's only known natural nuclear reactor, a phenomenon so improbable that when it was first proposed, many physicists assumed there must be an error. The conditions required were remarkably specific. The uranium deposit was rich enough in uranium-235, which was more abundant 2 billion years ago, because it decays faster than uranium-238, and was, therefore, a larger fraction of natural uranium at that time. Water acted as a moderator, slowing the neutrons produced by fission to the speed at which they could trigger additional fissions, and the system had a natural regulatory mechanism. When the reaction heated the water enough to boil it away, the moderating effect was lost and the reaction slowed. When the system cooled and water returned, the reaction restarted. The reactor pulsed in a slow, natural rhythm for hundreds of millennia. What the Oklo reactor tells us about the laws of physics is perhaps its most profound implication. The fine-tuning of nuclear physics is such that the fundamental constants have not measurably changed in 2 billion years. The reactor's behavior was governed by the same nuclear physics that operates in human-built reactors today, The This is important because some theories of cosmologies predict that the physical constants may change over cosmic time. The Oklo data places tight constraints on any such variation. The constants of physics were the same 2 billion years ago as they are today. A naturally occurring nuclear reactor running for hundreds of thousands of years, quietly in a forest of what is now Central Africa, 2 billion years before the first human being existed to notice it. The universe has been performing experiments we never planned. The butterfly effect and predictability. In 1960, meteorologist 61 Edward Lorenz was running a weather simulation on an early computer when he made a small shortcut. To rerun part of a simulation, he entered a starting value of 0.506 instead of the full stored value of 0.506127. He expected a simulation nearly identical to the original. What he got was a result that diverged dramatically. Within what represented a few weeks of simulated weather, the two runs bore no resemblance to each other. From this small accident came one of the most important insights in the history of science. Chaotic systems. Systems governed by perfectly deterministic laws can be so sensitive to their initial conditions that the tiniest difference in starting state produces completely different outcomes over time. Lorenz described this as the butterfly effect, the notion that a butterfly flapping its wings in Brazil might, through a chain of atmospheric events, eventually influence whether a tornado forms in Texas. The butterfly effect does not violate determinism. The atmosphere obeys physical laws precisely. If you knew every molecule's position and velocity with perfect precision, you could, in principle, calculate the weather exactly. The problem is that in practice, you never know the starting conditions with perfect precision. And in a chaotic system, the uncertainty in your knowledge, however small, expands exponentially over time until your predictions become worthless. The intrinsic predictability horizon for weather is approximately 2 weeks. Beyond that, no amount of additional data or computational power can substantially improve the forecast because the errors in our knowledge of the current state grow faster than our ability to shrink them. The atmosphere is deterministic, but practically unpredictable on timescales beyond a couple of weeks. Chaos is everywhere. The long-term orbits of planets in the solar system are chaotic. The timing of dripping faucets is chaotic. Heart rhythm, neural firing patterns, population dynamics in ecosystem, all exhibit chaotic features. The existence of chaos in deterministic systems means that prediction has fundamental limits, not just practical ones. A universe governed by fully deterministic laws can still be a universe that is, in the long run, deeply unpredictable. And in that unpredictability lives something that might, if you squint, look a little like freedom. Closing thoughts. The questions we have explored tonight are not failures of science. They are its frontier, the places where the known world ends and the unknown begins, marked not by emptiness, but by the most interesting and most contested territory in all of human inquiry. This There is something important in sitting with these questions, without reaching for premature answers. The history of science is full of mysteries that seemed insoluble for generations, and then yielded, sometimes to a sudden insight, sometimes to a new instrument, sometimes to a shift in conceptual framework, so profound that the question itself had to be reformulated before it could be answered. The questions that feel most unanswerable today may look, from the vantage of a century hence, like the obvious problems that were simply waiting for the right tool or the right mind. And there will always be new questions. New questions. This is the deepest truth about science as a project. It is not a march toward a final answer, but an ever-expanding engagement with a universe that is always more complex, more surprising, and more resistant to simple summary than the last generation of questions implied. You are made of atoms that were forged in the cores of stars that exploded billions of years before Earth existed. You are a temporary organization of matter that has become somehow aware of itself. You live in a universe that is 95% invisible to all of your instruments. You are conscious, and no one knows what consciousness is or how it arises. You dream, and no one is quite sure why. You listen to music, and your body responds with pleasure and with something that resembles awe for reasons that evolutionary biology cannot fully account for. These are not reasons for despair. They are the reasons this existence is worth paying attention to. The universe did not have to be interesting. It is interesting. Profoundly, inexhaustibly, mysteriously interesting. Sleep well, and wake up, as always, in the middle of the greatest mystery there is. A universe that confounds us is not a universe that has failed us. It is a universe that is larger than our current capacity to understand, which is to say, a universe worth the continued effort of inquiry. The questions we have explored tonight have occupied scientists and philosophers for generations. Some will be answered in your lifetime. Others may take centuries. A few may turn out to be unanswerable in principle, because they touch on the fundamental limits of what any mind embedded in the universe can know about the universe it is embedded in. That is all right. To sit at the edge of knowledge without flinching, to hold the question without demanding the answer, is one of the most distinctively human things there is. The universe made creatures capable of wondering about it. Whether it did so with any purpose, whether wonder was designed, or whether it emerged from blind physical processes, is itself one of the questions science has not answered. Wonder at the mystery is a reasonable response to the mystery. It is, in fact, the only honest one. Rest now. The universe will still be mysterious in the morning. There is one more thing worth saying as sleep approaches. Every mystery we explored tonight was discovered by someone who looked at something ordinary and nori, and asked a question that turned out not to have an ordinary answer. Who looked at the night sky and asked where the stars came from? Who looked at a patient sleeping and asked why? Who sat with an equation and noticed something strange in it that everyone else had passed over? Who heard a persistent hum that no instrument could find and refused to dismiss it as imaginary? Science advances through this quality of attention more than through any other single thing. Not certainty, not authority, not funding, not technology, though all of these help. Primarily through the willingness to notice that something doesn't quite add up, to stay with that noticing, and to follow it wherever it leads, even when it leads somewhere uncomfortable. You have spent time tonight with the places where the most careful, the most persistent, the most technically sophisticated inquiry humanity has yet achieved has arrived at a wall. These walls are not failures. They are the current edge of one of the greatest collect projects in human history. The Project Understanding. Lie. Passer. The project of understanding what this place is, and what we are, and how it all works. The mysteries are real. The inquiry is ongoing. And somewhere tonight, in a laboratory, or at a desk, or lying awake, thinking about a problem that won't resolve, someone is working on one of these questions. Tomorrow, they may find nothing, or they may find a thread. And if they pull the thread long enough, with enough patience and enough honesty about what they find, the world will look different in a way that cannot be undone. That is how it has always worked. That is how it will work again. Good night, and thank you for wondering.